Okay. Hi, everyone, and welcome to this very special edition of our scientific dialogue. It's an extraordinary honor today to be joined in one of the most brilliant minds in theoretical physics, Professor Juan Maldacena. He is the Calpe Feinberg Professor at the Institute for Advanced Study in Princeton and is globally renowned for his groundbreaking discovery for at the SCFT correspondence and cornerstone in our understanding of string theory and quantum gravity. He is studying this relationship further in the order of understanding the deep connection between black holes and quantum field theories. And he is also exploring the connection between string theory and cosmology. He has received numerous awards, including the Lorentz Medal, Dirac Medal, and the Albert Einstein Medal. Professor Maldacena, thank you so much for being here with us today.
Yeah, hello and hello everyone.
Thank you so much. So, first, Professor, to begin with, could you tell us what's first inspired you and interested in physics growing up in Argentina?
Yeah, so I grew up in Argentina, and when I was young, when I was in grade school, in high school, I was interested in how nature works, how technology works, and that somehow those questions got me interested into physics. And when I decided in Argentina, you have to decide at the end of high school which career to follow and where to go in the university, and I decided to go into physics. I was doubting between physics and engineering, and I decided to go to physics because I didn't know what it was about, so I decided to try it. If I didn't like it, I would switch to engineering, but I liked it and I stayed in physics.
Okay. Okay, thank you so much. So, to begin with the questions of your specialty on physics, I have three options and the difference between. We have three questions. What is the difference between general relativity and quantum mechanics? Second, we have what is the difference between black hole and wormhole? And finally, what is the difference between quantum gravity and string theory?
Um, okay, so gravity is the theory that Einstein developed. So that's the modern theory of gravity. It's also called general relativity. It's a theory where space-time is dynamical. It can be curved, and is curved by the matter that exists in that space-time. And in this way, Einstein described gravity. So Einstein's theory is a theory with many predictions, like black hole, the existence of black holes, the expanding universe, gravitational waves, and so on. But it's a classical theory. So classical theory means that there are deterministic equations that, given the space-time at some moment in time, you can then find the space-time everywhere. Um, and there is basically one space-time that describes the, the physics. Now, at the more or less same time that Einstein was developing relativity, other physicists, well, also Einstein himself, were developing the theory of quantum mechanics. So that theory was mainly developed to describe microscopic particles, such as atoms and molecules. And it's a new type of mechanics, a new type of dynamics, different from sort of Newtonian mechanics, which is what you probably learned in school. And it's a description of mechanical systems which is intrinsically probabilistic. So there are many options in principle for what the system could be doing, and when you go and measure, you find out, let's say, one of these possibilities, and you can only give the probability that something happens. So in that sense, that's one aspect in which it differs from classical physics.
Okay.
And yeah, so that's the difference between classic. And so we applied quantum mechanics mainly to small things, such as
Yeah, exactly. Quantum mechanics and string theory.
yeah, quantum mechanics for small things, and the best, so the most tested theory we have of quantum mechanics of elementary particle physics is a so-called standard model of particle physics. And then there are some speculations of what could be at the deeper levels, so at even shorter distances.
Okay.
Now, at very short distances, we expect that the effects of gravity become important, so that
Okay.
there should be like new particles associated to gravity, which we sometimes call the graviton. And the Einstein theory it's a theory that is difficult to quantize. It's difficult to find the quantum version. So for other theories, it was easier. So for example, for the theory of electrodynamics, right, there was a classical theory that Maxwell and others developed. And then in the 1930s, this theory was quantized, and then and then that quantization was understood further up in the 50s, and now we understand it very well. But for gravity, this type of method that was used for electromagnetism doesn't quite work, and so people developed other theories such as string theory, which is a possible quantization of gravity. So you should think of string theory as a possible measure of quantum gravity and quantum and sort of gravity and quantum mechanics, or a theory of a quantum mechanical space-time. That's another way of saying it.
Okay.
Now, you might ask, why do you care about this? So why do you care about this problem? This
Yeah.
very short distances, smaller than any distance we can measure today, much smaller than any distance we can measure today. And the issue is that the current laws that we understand are not valid at regions of very high space-time curvature, such as the
Yes.
interior of black holes, and perhaps more relevant for us would be the beginning of the universe. So when the whole
Okay.
universe was very small, right, then it had to be described using quantum mechanics. And already the theories we have today about the inflation and the early universe use some quantum effects. So some quantum effects that we can treat, but
Yeah.
if you go
The
into
inflation is it the result of quantum mechanics or general relativity? Because we have the one singularity in the Big Bang, and we can have the unification of these two theory, just like a black hole. There is a singularity inside.
yeah, that's the rough idea. So the now that sometimes cosmology is distinguished between the Big Bang phase, which is dominated by radiation, and some earlier period of inflation. But if you go even before inflation, then these quantum effects become important. So become more important. So they're already important during inflation, but they become even more important earlier. And that's one of the main motivations for understanding this theory, because we think that if we had this theory well understood, we would understand the beginning of the universe or what came before, if there was something that came before, and so
Okay. And the quantum gravity, what is really the difference between
between string theory and
initial?
quantum gravity. Well, quantum gravity is just any theory that puts together quantum mechanics and gravity, and
Okay.
string theory is a particular proposal, and
Okay.
but it's today is the most developed proposal and the really more
Yeah.
consistent
Okay.
proposal. It's still a theory under construction, so we there are some things we still don't know not how to describe in string theory. For example, this problem of the beginning of the universe is something we
Yeah.
cannot. We don't know how to describe it in string theory, so we don't understand the theory well enough to say what happened there.
Yeah.
But I would say it's the theory that is most advanced into the quantum gravity. So quantum gravity is like an objective. So finding this, you know, cool theory of space-time and quantum mechanics, and
Yeah. Exactly.
string theory is a
Okay.
proposal in this direction. Yeah.
Yes, I have this paper. It's you're mentioning. This is one of your most famous and the most frequently cited scientific article. Could you summarize it for us in few words?
Yeah, so this is a paper that relates so-called quantum field theories. So quantum field theories are theories of particles, interacting particles, and it relates that to theories of gravity. Um, and it, it, so the advantage is that you can describe a gravitational system, including quantum gravity and all that, by a theory that has no gravity. So it translates this problem, this mysterious problem of quantum gravity, to a problem in particle physics. Now, the idea is that the paper proposed this as a conjecture. So it's not a proof that is the same, but it's a conjecture. And since then, there was many other researchers worked on this topic and found more evidence for this conjecture. And but it's something we are still trying to understand. So it translated the problem of quantum gravity to a problem of finding the dictionary between what you calculate with gravity and what you can calculate using this well-defined quantum mechanical theory of the boundary. this well-defined quantum mechanical theory. The nature of the relationship is that there is some space-time and it has some interior region. Um, and then you imagine a surface very far away, and thank you for the drawing. And so there is gravity in the interior where the apples fall and so on. And there is a theory of interacting particles or qubits that are represented by the zeros and ones in that your picture. And those qubits describe the physics of the interior.
Okay, so I have another question about your paper.
Yeah.
You mentioned the Young-Mills theory in your
Yes.
article, which is one of unsolved prize problem. Could you explain briefly this theory and what problem it's trying to resolve?
Well, the Yang-Mills theory is a generalization of electrodynamics that we use to describe the strong interaction. So one example of a Yang-Mills theory is the theory we use to describe the strong interactions. Actually, we also use it for the weak interactions, so some of the fundamental interactions of nature. So in electrodynamics, there is only one photon, if you wish, but in this Yang-Mills theories, there are photons that are themselves charged under under these interactions. So we sometimes call it. We denote the charges of that this photon is called gluon is sensitive to. We call them colors sometimes. It's not really an actual color, but it's just a name people put for these variables. And so in those theories, the gluons can interact with each other, and they have a complicated dynamics. In nature, they have a complicated dynamics at low energies that is responsible for us not to be able to see this color chart. So everything that we see in the macroscopic world is color neutral. But yeah, so that's and proving this fact that everything that you will see is color neutral is related to this problem that you mentioned, this millennium problem. Just proving that if you start with almost at very short distances, these gluons are massless, and their interactions somehow generate a kind of mass scale and imply that the lowest energy excitations will be massive.
Okay.
So that's for the Yang-Mills theory applied to nature. So the version that appeared in my article is another version of Yang-Mills theory, which has
Super Young-Mills, I think.
yeah, it has this additional property of supersymmetry. This, for the purposes of our discussion, this is just a technical issue. So it's a simpler version, if you wish, of Yang-Mills theory, which is a bit more solvable and where the interactions are constant at all scales and has a slightly simpler physics, but still rich enough to describe some kind of gravitational system.
Okay, thanks. Your most celebrated contribution in the ADS-FT correspondence. This is the name of this your theory, the ADS-FT correspondence. For our auditors, could you briefly explain what it means and why it has been called the most reliable resolution of the holographic principle?
Well, it's a bridge between two different kinds of theories: the theories of gravity, or theories similar to Einstein theory, and theories of interacting particles. And it's a bridge that you can cross somehow in two different directions. So you can translate complicated problems in theories of particles to simpler problems in the gravity theory. And that's one reason people have studied it. And the other is just to learn about the theory of quantum gravity. So translate some problems which are hard to understand in quantum gravity to problems that are easier to understand in the theory of particles. Yeah, so that.
Okay. The idea that gravity in higher dimension space can be equivalent to quantum field theory on its lower dimensional boundary sounds almost magical. Did this idea come to you gradually, or was there a moment of sudden insight?
Well, I think it came somewhat gradually. So previously, myself and others were studying aspects of the connection between black holes and some objects called deep brain. So some we were studying black holes in string theory. Let me summarize. Using some modern techniques that people, in particular researcher called Joe Polchinski had discovered a couple of years earlier. And in that theory, it looked like there were two different ways of doing a calculation. So, and eventually, these two different ways translated into the calculation that you do in the interior in gravity and the calculation you do in the boundary theory, in the particle theory. So, and I think what I did in the paper was to isolate the precise relationship between the two things and the two ways of doing the calculation. And
Okay.
something that sort of kind of came gradually. And well, one important step was the realization that the symmetries of both systems were the same. So
Yeah. Okay. The implication of this safety are very vast. Do you believe this correspondence could eventually lead us to a full theory of quantum gravity?
well, that's my hope that the lessons that we learn through this relationship might help us develop a better theory of quantum gravity. I mean, one important limitation of our current understanding of ADS-FT or holography is that we understand it when we have special kinds of universes. So universes which have, if you wish, a cold region far away that is not expanding or contracting. So in particular, it does not describe our universe that had a beginning and has no visible boundary at least. So it's unclear whether our current understanding is useful for our, how the universe is, our universe we live in really is. So if you wish, it allows you to give you a complete description of quantum gravity for some other universes, not for the universe we want. One way to say it is that we made a sign mistake. So the dark energy in our universe is positive, and in these universes, the value of the dark energy is negative. And
Okay.
that's one difference, and it implies that the shape of the universe at long distances is different. So
Yeah, exactly.
in some sense, in these other universes, the universe expands as you go far away in space. Our universes expand as you go in time. So
I think we have the notion in this case, we have the space-time, LDS space-time and DS space-time. I think one is positive and the other is negative.
yeah, that's where the acronym comes from. So the first solution for an expanding universe with positive dark energy was found by De Sitter, a Dutch astronomer,
Exactly.
soon after general relativity. And anti-De Sitter just means it's the other sign. So that's the sign I was mentioning.
Exactly. Okay. You once suggested that an internal black hole is equivalent to an integrate quantum state. How does this connect to the famous AR equals APR conjecture? And how serious is this the idea that wormholes and entanglement are related?
Right. So, well, the eternal black hole is a funny solution of general relativity. It's not the solution for a collapsing black hole again. So our black holes that form in nature, they collapse. They are given by particular geometry. That outside is similar to the eternal black hole, but inside has matter. Right. That's the ordinary black holes that from collapse have some matter. Now, the eternal black hole is a solution with no matter inside, and it's the kind of solution that Schwarzschild found. So the first solution found for general relativity. And when it was properly understood, it is a solution that describes two black holes that are, let's say, very far away, but connected through the interior. So it's a kind of wormhole, but it's a wormhole that is not traversable. So if you try to go in through this wormhole, the wormhole stretches and collapses before you can cross it. But at some moment in time, the space connects between the two sides. And so if you are just outside one of these systems, it looks like a black hole. So it looks like two black holes. And the idea is that we should think of this. Well, first of all, in general, we think that a black hole is described as some quantum system that has some large number of qubits or degrees of freedom. And the idea is that this geometry would be what would result if those degrees of freedom or those qubits are entangled with each other in a particular entangled state. So that's the connection between, sometimes called ER equal to EPR. So Einstein, Podolsky, and Rosen wrote a famous paper showing that quantum mechanics is so weird that it allows this property of entanglement. So the idea that there are some correlations between distant systems which are somehow stronger than classical correlations. So here your picture is showing the fact that we could have two qubits, and if you that they are entangled in such a way that if you measure them, if you measure the right one to be in the one state, the left one will be in the zero state, and vice versa. So if they measure the one in the right to be in the zero state, the one in the left would be in the one state. So so if you look at only one, the answers look completely random. But if you look at both of them, we see that the answer is correlated. And I mean, that you can have in classical systems that are correlated. But what's interesting about entanglement is that you could do that measurement in sort of different bases that do not commute or that are subject to the uncertainty principle. And even though your choices that you make in one or the other are subject to the uncertainty principle, once you consider both of them, they're always correlated. So this is considered now to be a fundamental property of quantum mechanics. So that was what Einstein, Podolsky, and Rosen did. But in the same year, Einstein and Rosen, so two of the collaborators of the previous discussion, they were looking at this Schwarzschild solution, at this what you call the eternal black hole, and thought that for a different reason. They thought that they basically noticed this fact that I mentioned before, that the solution was really describing a geometry where the two sides were connected to each other. So that space-time connection sometimes is called Einstein-Rosen bridge, in honor of Einstein and Rosen. Yeah, so these were two different things. I'm sure they thought these were two different things, but now we think that they are connected. So.
Okay. So I have this paper. It's your paper, Reason for Integrity Black Hole. I think this paper talk about this AR equals APR and this connection between wormholes. Yeah, this is.
Yeah, that's right. So I think the idea in that paper was to use this relationship between the entanglement and wormhole to address some paradoxes of black holes, and we also thought that maybe this could be a general principle that could arise to any entangled system. That to any entangled system, that any entangled system is joined by a tiny wormhole. And this is a more speculative idea because we don't understand quantum gravity well enough to know whether this is correct or not.
Okay, the black hole information paradox has puzzled physicists for decades. Do you think we are getting closer to a definitive resolution, or is still just an open puzzle field of ideas?
Well, I think I think it's getting more and more understood, and as we understand one aspect of it, then there are some other aspects that we don't understand. I feel it's been a very useful source of theoretical problems and sort of paradoxes that have been helpful for the development of the theory. So ADS-CFT, if you accept it, then it tells you the information comes out, but it doesn't give you a picture from the bulk point of view. And nowadays, in the last few years, through the work of many people, such as Ahmed Almeri and other people, it was understood how to solve some aspects of the information paradox just from the bulk point of view. So just purely using gravity without using this auxiliary quantum system or any conjecture duality, just from the rules of the game of quantum gravity and the effects of new topologies, so similar to wormhole topologies. They explain somehow how information manages to come out and so on. So I think we made a lot of progress, especially in the last few years, in the last 4 or 5 years. So maybe 6 years.
Okay.
2019 were the very important papers, and then this new understanding raises other paradoxes, and so people now are trying to understand these paradoxes, these other problems, so I think maybe one way to think about this black hole information problem is I think it is playing a role similar to the famous elevator problem that Einstein was thinking about, the problem where he was imagining an elevator that was falling, and then a beam of light that in from the point of view of the person in the elevator, the beam of light goes straight. But from the point of view of the person outside, because the elevator is accelerating, the beam of light is deflected downwards. And from this, he deduced that light should be bent by the gravitational field. And so that was an example where, by thinking about the problem from two different points of view, so from the two different observers, the one who falls in and the one who stays outside, he could deduce something interesting about gravity. Now, in this, the black hole information paradox is similar in the sense that it's about two different observers. So there's one that remains outside the black hole, and then there is another one that falls into the black hole. And they describe the physics in different ways. So the description from the outside point of view looks very strange. So it looks like the observer who falls in sort of gets burnt up by very hot, some radiation in the black hole horizon, but the observer who falls in perfectly fine. And the question is how to put together these two different perspectives, and that's what we are understanding how to do. So, but I would say we still haven't understood it completely. So, in particular, how to really make the two really compatible. And I think part of the understanding the black hole problem is to understand what happens at the singularity inside the black hole. And that's something we haven't understood. So, and I think that's important because if we understand what happens in the singularity, maybe we'll be able to also learn some lessons for cosmology and understand what happens in cosmology. And that's the major motivation, I think, to study black holes. So there are two motivations we can say. One is just to understand problems in quantum gravity. So, well, it's clear problems where we need to develop the theory, so that it's useful for us to develop the theory. And second is that there is the singularity that is somewhat similar to the singularity at the beginning of the universe, so we could also offer some lessons in cosmology.
Okay.
And I would say that these lessons for cosmology have already happened in some sense. So there is a phenomenon that was discovered in the context of black holes, which is the phenomenon of Hawking radiation. So it's a theoretical prediction that that black holes emit thermal radiation, and it's an effect that is very small for astrophysical black holes, so it hasn't been seen in nature. But there is a similar phenomenon that happens when you have an expanding universe, and so when you have an expanding universe, again, that universe has a temperature, and again, the temperature for the universe today is very small and not observable, but we think that in the beginning of the universe there was a period of inflation, and in that period we think the temperature was much higher and led to sort of thermal fluctuations or quantum fluctuations that then were the seed for cosmological fluctuations and the formation of structures and galaxies and so on. So in that case, we are really using a very similar effect to describe a feature of our universe. So that's an example of some lessons that were learned in black holes and then transferred to cosmology. And we hope that by this more deeper understanding that we are learning today, especially in the last few years, we'll hopefully be able to translate some of those to cosmology. But that hasn't happened yet. That's our main hope. Yeah.
Oh, it's very you are very explaining this information paradox because we have some students talk more about this puzzle, this paradox, and I think. Do you think we can solve it using mathematics or experimentally physics?
Well, I'm a theorist, so I think we can solve it using mathematics. But it might be that with if we were able to do experiments, we probably would solve it much faster. So if we were able to do experiments with actual black holes. Now, I think, as I was saying, for the black holes that exist in nature, those black holes are so big that they are very well described by the classical theory, and these effects we are discussing are irrelevant. And producing very small black holes where these effects would be more drastic it's technologically impossible right now, at least with the present technology and with the technology that we'll have in the next few years. Now, in terms of experimental verification or exploration of some of these ideas, I think the most interesting aspect is this connection between quantum theories and gravity, because now you can somehow engineer a complex quantum system that could have a gravity description, an emergent gravity description, similar to what we have in this ADS-CFT or in this duality we were discussing in the beginning. And that's something that maybe could be done in the next few years. So that, and I think those things, well, they will certainly test, and will be more evidence for this relationship. But in addition, it might raise new questions, and it might help us explore it much faster, and perhaps we'll be able to understand it well enough that we'll make dramatic progress also. So I would say that's the main experimental frontier right now. So trying to use quantum computers or quantum simulations to simulate these complex systems that could have a gravitational description.
Okay. So some scientists argue that the holographic principle could play even to our own universe, which isn't anti de Sitter. How realistic is it to play at the SFT ideas beyond at the spaces?
Well, I mean, in some sense, the Sitter, sort of an expanding universe that expands forever, has a structure somewhat similar to the other case. So there is some region far away in the future, and so there might be some statistical system that lives in the far future that could describe all observations that one could imagine. But we don't have any examples, so we don't know whether that's true, or if the examples we have are so idealized that we don't know whether they're really. But we don't have any example that involves Einstein gravity and Einstein theory of gravity. And yeah, so that's one avenue, and so people are exploring also other avenues for trying to understand
Okay.
how this.
And your work with Leonard Susskind, you propose.
Yeah, we were cut off. We were cut off a little bit. So
Yeah. I'm sorry.
no
And
problem.
your work with Leonard Susskind, you proposed that entanglement particle might be connected by wormholes. If
Yeah.
true, could this change how we think about space-time itself?
Yeah. So I think that this example was an extreme case of something that people were also thinking about. So the idea of the idea that in complex quantum systems, space-time arises from entanglement, and that entanglement plays an important role in the emergence of space-time. So I would say that ideas centered around that are very important and are part of also the recent progress around black holes. So yeah, this is, I think, one aspect related to the emergence of space-time, and then people are also exploring other further aspects that involve not only entanglement but also complexity and quantum complexity. But these are some further ideas.
Okay. Recently, I will show you one of this paper. Recently, a scientific article was published suggesting the
Yeah.
possibility of testing the existence of wormholes related to quantum gravity using quantum entanglement and quantum computing. What do you think of this discovery? How have we truly come closer to unifying gravity and quantum fields with experience?
Well, I think so. So there was this example of the eternal black hole that we mentioned before, and then there was a very important observation by Gao, Jeffries, and Wall, some other researchers, that realized that if you have these two black holes and you send some information between the two, or you bring them a little closer, then the wormhole that exists can be traversable. So that means you can send a signal through this wormhole. And what this paper you're showing me did was to find very, very simple systems where there is a similar phenomenon. So there's a similar phenomenon in sort of simpler systems that it's a little unclear whether we should describe them as gravitational systems, but where there is a kind of teleportation similar to what exists in gravitational systems. I would I guess I forgot to mention one important thing. So when you have these two black holes and the wormhole that comes from entanglement, and you bring them close together, then you can send signals through the wormhole. And the process by which these signals travel is closely related to the way in which you can send information using a process called quantum teleportation. So quantum teleportation is a way to send signals that uses entanglement in a crucial way. Um, and it's a method for sending, let's say, secret messages. So you share an entangled pair, and then you send an unrelated piece of information, and the information somehow appears in the other person using the entanglement, the desired information. And this can be used to send informations in secret. So, and in the gravitational context, this information somehow goes in secretly compared to people who are outside because it goes through this wormhole. Um, well, I guess I
Okay.
summarized that perhaps too much, but
Okay.
hopefully
Thanks.
everyone understands it.
As I mean,
But yeah, so what these papers have been doing is to understand the simplest systems that could lead to this form of teleportation, and people are busy
yeah.
trying to uh, reproduce this very simple form of teleportation in the lab. And in fact, there were some proposed
Okay.
results that the people who claim to have observed it, and then people say no,
Okay.
it's
Thanks.
not complex enough. So there is a whole dialogue, interesting dialogue occurring now between experiments and experimenters and
Okay.
theory in this context.
Okay. As a mentor and educator, what advice do you give to young physicists who aspire to explore the deep questions of the universe?
Well, I think the main important thing is to understand well all the principles of physics, to understand the physics that is known today. So it's hard to make progress, understanding the big questions of the future without having understood what's understood today. And and then, so once you understand what's understood today, you also have to understand what is not understood today, and where the open
Yeah.
questions are. And there are lots of open questions in physics. We've been discussing some of the open questions in very fundamental physics of the basic laws of the universe. And yeah, so that's what.
Okay. You studied in the legendary physicists like Callan and worked alongside grand mind like Edward Witten. How did this collaboration shape your scientific journey?
Well, I think it was wonderful. I mean, studying with Kirk Callan, who was one of the developers of creators of the standard model, who understood so many things. He had, great physical insight, and could get to the important questions very quickly. And also, Ed Witten is absolutely wonderful, amazing. I mean, his knowledge of math and physics and creativity is really outstanding. So it was very. I was very very fortunate to be to be around them.
Yeah, okay. Physics today is expanding across borders from quantum computer to cosmology. What area do you believe hold the next big surprises?
Um, well, I hope my biggest hope is that we detect gravity waves from inflation. So these are these are this is something that would be observed by looking at the polarization of the cosmic microwave background, and would
Okay.
be a signal that um, gravity waves were produced during the inflationary period. I think this is
Okay.
particularly exciting because it would tell us first that gravity is quantized. There is really quantum.
Uh,
This, according to inflation, this would be produced by quantum fluctuations, but also it would be a really good test of inflation, and it will tell us exactly at what scale inflation happened. So how rapidly the universe was expanding during the inflationary period, and yeah, so that's I think
okay. I think we have some notion, more notion about inflation, preheating inflation, reheating inflation. I think there is some notion about this, the Big Bang theory.
Um,
Do you
well, I
have
mean,
any
there are many experiments trying to measure the cosmic microwave background. So both from
Yeah,
the
exactly.
ground, from observatory.
WMAP, Kobe, Planck. Yeah,
Yeah,
exactly.
those were the satellites that were sent
Yeah.
a few years ago. But now there are some more modern detectors that are from the ground.
Okay.
Uh, there is one in the Atacama Desert, so in Chile, some
Okay.
very high plateau that is particularly good for that. And people are also thinking of new satellites that will be specifically designed to measure polarization.
And the gravitational waves, I think we have some projects related to NASA collaboration with ESA and the others. The name of this collaboration, LISA, the project of
Right.
LISA.
Right.
Do you think
Yeah,
this
no, this
can be?
this is well, this is will be very exciting, very interesting, and measure sort of gravitational waves in a different frequency range. And those are similar. I mean, in some sense, conceptually similar to the ones that LIGO is measuring at the at a different frequency range. It will be sensitive to other kinds of objects and so on. From the point of view of studying quantum gravity, I'm not sure whether that. I mean, but that will be that will have a different impact. But it will be very interesting for astrophysics. It might show different kinds of objects in the cosmos. So I'm not saying that. Of course, it will be very exciting if LISA happens. Yeah.
Yeah, I think some societies try to invent black holes in the labs. Do you think we will get that in the future?
Yeah, so this idea of black holes in the lab is the idea that you engineer some or you design some complex quantum system that has a gravity description in an alternative gravity description. I think that would be the way you would make something that looks like a black hole in the lab. You could question whether this is real black hole or is a simulation of a black hole or a black hole in a different universe. I think
Okay.
it is all those things. Um, yeah, it would not be a black hole of our four-dimensional gravity and our four-dimensional space-time. I think
Okay.
doing that in the lab would be much more difficult.
Okay. Thanks. Theoretical physics often feels very philosophical. Do you think there is still a place for beauty and elegance in today's physics, or is just purely about mathematical consistency?
Well, I think the main guide is mathematical consistency, and usually when people find consistent formulas, they think they are beautiful. So I think I think it's beautiful when it works, and of course the previous all the theories of physics that we have now, or people say, oh, they are very beautiful, but I think they're very beautiful precisely because they
Okay.
work, and they're surprisingly simple. I mean, it's quite. Surprising how simple the basic laws of nature are compared to the diversity of phenomena that you can explain with them. So I think that this idea that the underlying laws of nature should be relatively simple is something that has uh, has happened during the history of science, or at least the history of fundamental physics.
Okay. Do you think that quantum gravity will develop the field of artificial intelligence?
Um, well, I'm not sure. I mean, there are some vague parallels between the way we understand quantum gravity as coming from entanglement and the way that, let's say, knowledge comes out of neural networks in artificial
Ah,
intelligence. But these are some vague parallels. I don't know whether they will be useful. That there will be a useful connection. There might be, but I think the connection
ah.
so far is too vague to have any concrete use in any, yeah, at least
But I
in that
think
direction.
there is okay. But I think there is some way to use quantum gravity in the AI artificial intelligence because we have this paper and we can have more in the future. What do you think?
Well, I think there is a question of whether, I mean, of course, it's probably true that AI might be useful for quantum gravity research, as it would be useful for research in many other areas. Um, I think your question was mainly whether some of the basic core
Yeah.
ideas of quantum gravity might be useful. I don't
Okay.
know. I mean,
Exactly.
the math and methods that are used are similar, and in fact, some people that have worked in quantum gravity are now working in AI. But I yeah, I don't know whether there will be a deeper
Okay.
connection. I suspect there will be. I mean, if you ask me to bet, yeah, I would bet that there will be.
Okay.
But I don't.
Do you, Do you think artificial intelligence will change the job of a physicist?
Probably, yeah. I mean, I think we can compare it to when computers came, right? So before, the job of a scientist was doing calculations was a very important part of the job. But then when computers came, a lot of calculations are done with computers now, and people can use these calculations to discover new phenomena, right? For example, the study of chaos and so on, and fractals, all that was greatly helped by computers. And I think AI is very significant, it's a very big advance in computation, so we probably will. Also, we will use it in some new ways. That I
Okay.
guess I'm
Fine.
from the pre-AI world, so I I don't know in the future we'll use it in a
Okay.
wonderful way. And there will be many things that we currently do today that probably will not be done by us or done by the machines. But um, I guess we'll probably find new things to do.
Okay. Finally, if you could travel back in time to speak with Einstein, what single question would you most want to ask him?
Well, I would think I would ask him what he thinks about the R equal to EPR.
Ah, okay.
Yeah, about the connection between wormholes and entanglement, and more generally about the connection between quantum mechanics and gravity.
Okay. Thank you so much. We will pass to the questions of auditants. We have first, I think, partition. Okay. This question: How does partition function appear with a factor of event rho is should necessarily to be positive? And what is your opinion on the study of dimensionality called it's possible to be solution to be a solution?
Okay, I'm not sure I understood the question.
Also,
It sounds like a technical question about
yeah,
some computation in gravity that I don't
yeah,
understand.
exactly. I think, but okay, we pass to other question. Maldacena's at the SFT correspondence equation are extremely complex mathematical technically. Do you have any comments about this?
Well, they are complex, but they are similarly complex to other equations that people sometimes think about in physics. So, I mean, if you think about material and trying to 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 predict the properties of a material from the electrons and the nuclei and so on, that those systems can be very complex many times, and the equations are complex in a similar way. So,
Okay. I think this question talk about the partition function. Do you have any very simple explanation about this partition function?
well, I don't know what the person is referring to, but a partition function is sum over possibilities. It's something that appears in statistical physics, summarizing.
Exactly.
Um,
Yeah.
Doing a sum over various options is a concept in statistical physics, and it's related to probabilities, and so it should be positive because it's a sum of positive quantities. Now, sometimes in gravity we compute things which we think might be partition functions in the more fundamental theory, so that they might be positive, but sometimes the gravity computation gives us something negative, and then we have to explain that. Uh, we have to explain why that happens. Maybe we made a mistake in the gravity computation, or we made a mistake of translation. And yeah, so we have several situations where that happens, and we are trying to understand.
Okay. I have another question. Hi, Professor Maldacena. It's possible to build a version of string theory that is fundamentally non-symmetric.
Yeah, I think what the person meant that it's not supersymmetric. So
Non-symmetric, I
so
think.
I think what
Supersymmetric.
yeah, I think the question was that
Yeah.
whether it's not supersymmetric. So supersymmetry is a particular symmetry that
Supersymmetric,
relates
exactly.
bosons and fermions, so two types of matter particles. And the best understood string theories that we have today are supersymmetric, at least are supersymmetric at very short distances. And there are string theories people have proposed that are not supersymmetric. They either exist in very low number of dimensions, or even if they exist in large number of dimensions, they might have some instability, so that the simplest vacuum is unstable. And so those are less well understood. So, but I think it is possible that there are more string theories that are not supersymmetric.
Okay, I have another more question. Hi, question about the cosmic inflation. Is it an effective theory to describe the process of the universe creation? I think.
It's most about describing what happens. Let's say if you say about the creation moment. So after creation, there is this period of inflation
Yeah,
that somehow prepares the initial conditions for what we later call the Big Bang phase, or the phase that
yeah.
is dominated by radiation in the very early universe. So it's and it sets up sort of uniform or fairly uniform initial conditions with small fluctuations, and that's what inflation does. So inflation solves some problems of the previous Big Bang, what's usually called the hot Big Bang cosmology, but it leaves some other problems unsolved. So of what happened earlier. So
Yeah. Another question. I think we have three last questions. How would you explain non-Euclidean geometry to a higher scholar?
well, Euclidean geometry is the geometry of a plane, right? So you lived in a plane that would be the Euclidean geometry. Non-Euclidean geometry is a geometry of not the plane, but let's say, for example, the sphere. So if we live on the surface of the Earth, the geometry of the surface of the Earth is not Euclidean. It's a curve. It's just the curvature of the surface. So relationships that are true on the plane are not true on the sphere. So, for example, if you have a triangle with three straight lines, the sum of the angles sums 180 degrees, right? Um, However, if you have a triangle on the sphere made out of arcs, which are the analog of straight lines in the sphere, the sum of the angles can be different, can be bigger than 180.
Okay. Is there a future for the loop quantum gravity? Would you recommend researchers pursue it?
Well, the loop quantum gravity is some other idea for quantum gravity, for quantizing gravity that I would say is less developed than string theory and less, let's say, the internal consistency of the theory is more questionable than the one in string theory. So, string theory has the advantage of reproducing the Einstein theory of gravity in the low energy limit, but that is not a property that we've understood for the loop quantum gravity. Now, it might be that some ideas that people are exploring in this direction then find their place in a more complete theory. So, I, yeah,
Okay.
you should do research
If
you find interesting.
Yeah, if the RDS safety is only well definited is spaces with negative curvature, which we want to observe, what just justified its central role and discussions about quantum gravity and black holes in our real universe.
Um, well, sometimes I think if there was a version of ADS-CFT with positive cosmological constant, everyone would be discussing that, right? Um, Uh, the reason we are discussing this version with negative cosmological constant and is because it's the only case we understand. So we understand well enough. So we have more precise formulas for this case, and so we studied this as a toy model, and we hope that some of the lessons we learn from this case are valid also in the case of the expanding universe. Now, the question also involves black holes. Now, we think that properties of small black holes should not depend too much whether they are in a universe which is expanding or a universe which is curved with this negative curvature where the universe is flat. So we believe that they should be similar in all cases. So by studying the properties of black holes in in the case of anti-de Sitter, we think that we'll learn some universal properties of black holes that are valid more generally.
Okay. I want to study the SFT theory. How can I start?
Um, well, I think depends on what your background is. First, you will have to understand basically most of current physics. So quantum field theory, quantum mechanics, general relativity. So you need all those prerequisites, and then you can go online and find reviews, and you could, in principle, understand it.
Okay, I have this question. Can can we make a connection or bridge between the safety theory and donic objects? Donic objects, it's I think it's
Yes,
unification
yes,
of
yes. Yes,
magnetic charge.
right. Well, first of all, in nature we have measured electric charges, but we haven't never measured the magnetic charge or magnetic monopole charge. And we think that in a theory of quantum gravity, we should always have electrically charged particles. If we have electrically charged particles, we should also have magnetically charged particles. And once we have the two possible charges, we can also have particles that carry both electric and magnetic charges. That's what dion means in this sentence. And in all the examples that we have of ADS CFT, we always have both types of particles. I mean, we have electrically charged and magnetically charged and ionic charges, and we think that that's a general property of a theory of quantum gravity. And so that it
Okay.
should be possible to have magnetically charged particles in nature. That's an extrapolation from the lessons we've learned, but that's perhaps one of the most solid lessons that we've learned, is that there should be some magnetically charged particles. Now, that doesn't mean they were produced in the early universe and that they exist around, but that they should be possible as excitations.
Okay, this is the last question. Okay. Okay, I think. Okay, Professor, given the thermodynamics, the thermodynamics properties of black holes and the role of the entropy in the field theories, can we say that gravity is an emergent phenomenon from a non-gravitational quantum system?
Um, well, I'm not sure we can say just from those two things. I mean, those properties of entropy and properties of black holes are certainly consistent with these ideas of immersion, but they don't necessarily imply them. So they don't imply emergence. So this idea of emergent gravity, I think it's most clear in the context of this ADS-CFT, where you really have the boundary theory from which gravity is supposed to emerge. Um, and But we think that even in cases where we don't have the fundamental degrees of freedom, the idea is that the fundamental degrees of freedom might not be local in space-time and might exist in some more abstract space, and then the gravity in that space-time somehow emerges from the more fundamental degrees of freedom. So that's the idea of emergence, and exactly what the rules are for this more general case, we don't know, and people are certainly exploring them.
So thank you so much, Professor Maldacena. It has been a true privilege speaking with you today. Your insights into the nature of space-time, black holes, and quantum reality continue to inspire physicists and dreamers alike around the world. Thank you for sharing your time and wisdom with us. Thank you so much, Professor.
Sure. Thank you very much. Best wishes to
To
you and to everyone who was listening.
Thank you so much, Chuck. To our auditors, thank you for joining us. Stay curious and keep exploring the wonder of the universe. Thank you so much.
Okay.
Goodbye. Okay.